Great. Thank you, everybody. Thank you for coming to this workshop. The morning was tremendously exciting. We had disagreement from the start.
Recording in progress.
The nature of reward, is it all about extrinsic reward? Is it about intrinsic reward? Is intrinsic reward just, does it occur because of only one scalar extrinsic reward? I hope that we keep disagreeing. I recently heard a quote from, I don't know how to say his first name correctly, but Giri Buzakian, and he said, oops. No echo? Cool. He said he'd like to state his theories in really aggressive ways to provoke people to disagree with him, because that's how you can get somewhere. And it's not about being right, it's about moving the field forward. So here's a question. Learning the piano is hard. It requires a lot of effort and it takes a long time. And the entire time you could be doing something less effortful, less frustrating, and most likely more immediately rewarding. So how and why do we choose to learn to play the piano? Well, between being a skillful piano player and not being one, I'm sure most people in this room would say that they prefer to be a skillful pianist. It's definitely worth it in the end. But the question deals with the journey there, the trajectory to being a good piano player. Why do we go to school for so long? Or learn how to type somewhat properly instead of hunting and pecking? Why does a rat learn a perceptual task when it could randomly guess indefinitely and get a higher initial reward rate? This question illustrates a general problem in our fields spanning psychology, cognitive science, neuroscience, machine learning research. Let's say that you have two possible tasks available. One with a higher initial reward rate and another with a lower initial reward rate, but which could get to a higher reward rate later. Choosing task B is advantageous, or normative, one could say, because it will lead to a higher cumulative reward than task A. How does a decision maker choose or know to choose and continue to choose task B? Note that tasks here are abstract. They could also be strategies for the same task, such as taking the time to learn to type properly or passively getting better through hunting and pecking. Now, why is this problem difficult? Because it requires, to some extent, the prediction that task or strategy B will pan out while incurring reward losses, or at least opportunity costs, before it does. This is a general problem because it shows up everywhere, and numerous different approaches have been proposed across different fields. This is by no means an exhaustive list, but merely a smattering to give you an idea. Let's start with how this problem is similar to explore-exploit in RL. First, exploration can be random, as in an epsilon greedy algorithm, or the more sophisticated Thompson sampling, or it can be directed, as with an upper confidence bound algorithm, where uncertainty is in and of itself valuable. In an RL context, an agent would discover strategy B through exploration. Although note that to reap the benefits of B, it needs to be repeatedly chosen over A before it starts to pay off, which is more closely related to an exploitation of the exploratory strategy rather than just classical exploration. One could, however, say that an agent could treat exploring strategy B as an option, and thus learning to do it over option space. There's also the approach of deep exploration that is related, to when an agent will simulate a small number of deep trajectories. One could be only strategy B or only strategy A, as opposed to exploring the entire space, which could be intractable. Recent work has in fact found that deep exploration blurs the divide between random and directed exploration. There's also the approach of successor representations, where you change the entire value function to reflect that the value of a certain action also includes the subsequent actions that it allows. On the more cognitive end of things, the concept of curiosity predicts a drive towards uncertainty reduction. This is similar to an intrinsic value of information, which is related to the value of effort. Another potential solution to this problem, where a task that is more difficult is intrinsically more valuable, perhaps could be because of some long-run prior that doing hard stuff eventually leads to good outcomes. There could also be an intrinsic value of learning, which again could be a heuristic value there to nudge the agent towards strategy B. The advantage of framing the problem this way is that it simplifies the computations needed for an agent to choose a task that would only become favorable in the future. With the examples I gave you before, the heavy lifting is done by the computation. In this case, you're just pushing it all to, for instance, like a Markov type algorithm where you just upregulate rewards. The truth is that all these theories are probably true to some extent and under some conditions. But mechanistically, in our minds, how does this happen? So the work that I'll describe follows from what I mentioned and much more. But I'll try to highlight a few key aspects to orient you, because I feel like the challenge that we have in the general field of learning is relating our work to the work of those around us. So it fits within the broader context of look-ahead models. And this is, I know it's very general, but it highlights how your behavior is strongly affected by how long you expect to be doing something. Not only that, but when you are evaluating possible past, possible future choices depend on past choices that you have made. And this is, again, like a really fundamental idea. Here, I'm just citing the initial successor representation dissertation. From a mechanistic point of view, it relates to the idea of developing shared versus separated representations in network models. This is the idea of parallel distributed processing. Balancing the efficiency of learning several tasks quickly and being able to do them simultaneously. And finally, it uses the concept of cognitive control to manage this conflict between immediate and future reward. And we heard, for instance, Jackie Gottlieb talk about control briefly. I know that this is mostly neuroscientists, but control is very important to psychology. Crucially, though, it will explicitly consider possible learning functions when deciding which task or strategy to pick. And if you take anything away from this talk, it's just that I believe that it's extremely important for an agent to be able to consider how it can change itself in relation to the world based on its actions. So let's hop back in and consider that idea of a learning function. Let's say that our decision maker has some sort of automaticity or skill that describes how good it is at a task. In a perceptual context, like in the drift diffusion model, this could be akin to its signal-to-noise ratio. So in this case, strategy B leads to a faster increase in automaticity. The better its automaticity, the more reward it can harvest from the task at hand. Framed like this, by choosing strategy B, the decision maker is investing potential rewards in order to improve its automaticity to reap larger rewards in the future. I'd like to propose that this problem can theoretically be solved through the use of cognitive control. Cognitive control is the general concept for how one allocates mental resources towards goal-directed behavior, often overriding default behavior. So let's just do a quick exercise. Let's employ it. So please read aloud, and it'll be fun if everybody does it, the word that appears on the screen. That's easy, right? Now, please name the color of the word on the screen. Harder, right? Doing so requires control to override the default behavior of reading. And I purposely chosen a Stroop task here because I guess the most elegant first network model of cognitive control was a Stroop network model. So I promise you that control isn't just a fuzzy verbal psychology theory. There are really nice quantitative theories around it. And one specifically is the expected value of control theory, upon which this work is based. So one thing you experience with the Stroop task is that control is effortful, it's costly. And there are many debates as to why this is. The EVC theory posits that control is not intrinsically effortful, but rather that perceived effort is a reflection of the opportunity costs required but incurred while applying control to one task as opposed to all the other things you could be doing. So just to give you an example, if I'm studying really hard from a math textbook, the reason it becomes harder and harder over time is because I'm not playing video games, I'm not eating, I'm not doing a bunch of other stuff. Applying control to a task leads to rewards in that task. Oh, so this is the cost function. Let's just assume it's exponential the more you apply to any one task. Applying control to a task leads to rewards in that task. For example, retaining more information while studying if you are actually really focused. As such, control should be allocated in proportion to its expected value, which is the difference between the payoff and the cost. This leads to an optimal amount of control allocated to a particular task. And that can give you what that optimal value would be and how much control that requires. Now, although this theory is very general, in the past, the EVC has been applied to situations where the environment can be approximated to be static. Importantly, so is the agent. But what if the agent is not necessarily static? What if the agent can learn? And what if control allocation can take this into account? So I extended the EVC framework to where an agent can learn. The question is, can we use this EVC algorithm, which essentially is just putting together utility maximization and reinforcement learning, that is choosing optimal control signals based on payoff versus cost, in order to have an agent learn on its own without resorting to any intrinsic reward, such as the value of effort or information or learning or any of that stuff. Only an extrinsic reward available on a task, at least the agent's prediction of extrinsic reward, because this could also be an agent's own model of where it could go based on its control allocation. So here's a framework. Just like before, let's say that you have two tasks available, a cyan task and a red task. The cyan task is learnable. As you can see there, you improve your automaticity the more times you choose it, and your static task is stable. It doesn't matter how many times you choose it, you have some stable level of automaticity on it. Now, let's define an accuracy function at a task that depends on two things. One is the amount of control that you use, and the other is your current automaticity. So if we look at the red curve first, the static task, you have some accuracy curve there that gets higher the more control you allocate. So even at stuff that you can improve upon, if you try harder, you can get a little bit better. Now, the cyan curve there are many cyan curves because this is capturing, for instance, different points in time during a learnable task. When you're not really good at the task, you can see that your automaticity curve, if you look at the bottom one, is actually lower for the same amount of control compared to the red task. But as you get better, you can apply the same amount of control for a lot higher accuracy. So in that sense, it's normative. It's just like being at the state of being good at piano. But how do I get there? So let's just take one of these here and apply it to the framework I said before. So for any one level of automaticity, you can define an optimal control signal. But not only that. So in this case here that I've shown you, this could be thought of as an expected value of control without considering any future outcome. So you can extend this to a situation where you're not just looking at the greedy case, which is the word I'm going to use for just considering now and not considering future states, versus considering future states. So why is that important? Because if I only consider the greedy case, then my choice between choosing a learnable task or static task is going to be very different than if I take into account the fact that I can improve at the learnable task. So I can go back. Oops, we'll get it later. Okay, so now I'm going to show you essentially two ways to visualize a greedy task versus a greedy EVC algorithm versus one that considers future value. And this is where the importance of horizon comes in. So this is a greedy model for several different automaticities. So what you do here in the EVC framework is you look at how high the value is and then choose the task that has the highest value. So if you were starting to compare these two tasks, yes. So the red task here versus the beginning of the learnable task, you'd see that the red task has a higher value to the beginning of the learnable task. So you should choose the red task. Now you saw the consequences of that. you're going to be stuck in that local minimum where you can't improve. It does have a higher value at the beginning, but if you did know the other task, then you get to a much higher value. So how do you get from here to here if you're greedy? Now I'm going to show you just trial one of comparing these two models. So solid lines here represent the greedy model, and the dashed lines represent what I'm calling the EVCL, which is just the model that considers future discounted expected value. So here, like I showed you, you should choose the red task or the cyan task. But if you take into account future states, if you take into account the fact that the agent can learn, now this value is higher than this one, so the agent should choose this task. Now, briefly, this is how it works. So we've implemented it as a dense computation where you first compare the two tasks that you have available, you compare their EVC, and you select the task and control signal, and so on and so forth. But in order for me to compare the EVC of task L versus task S here, I need to have an estimate of what this entire set of trajectories can look like. Not only that, let's say I'm on trial 3. My state at trial 3 depends on the choices that I made before. If I chose the static task for the first 3 trials, my automaticity for the learnable task is going to be different than if I had chosen the learnable task 3 times. So it's a complex problem. And we posed it here densely, just almost facetiously to bring forth how complicated the problem is. Obviously, this needs some sort of heuristic, some sort of better estimation, but this is essentially the problem that we face. So if we framed it graphically like this, let's say you have 6 trials available, 2 tasks. That means you have 2 to the 6th possible choices ahead of you through the 6 trials. You choose the one that has the highest, and then go iteratively from there. So if you keep doing that all the way to trial 6, you find that the agent chooses the learnable task every time. So this shows, I'm going to show you now that the EVCL can normatively account for the value of learning. So if we look at the control signal over time for the greedy agent versus the learning agent, we find that the learning agent has to invest more control at the beginning, which is not good because it's expensive. But as it gets better, it can get away with less and less control for higher and higher accuracy. And if we look at the reward, it starts out with a lower instantaneous reward and ends up at a higher instantaneous reward. And if you look at cumulative reward, again, you see the same thing. So this essentially is the normative argument for why there is a value to learn. Now, this simple model depends on the same things that you see in many learning algorithms like RL, horizon, learning rate, and future value. These all affect what happens. So let's say you have a horizon of 5 trials. So this gamma here is your discount factor. So if it's 0, it means you don't consider the future. If it's 1, it means you perfectly account for future value. So when you have a gamma of 0, it doesn't matter how fast you learn. You're always going to choose the static task because you're not taking into account the fact that you can improve. As your gamma gets higher, you actually, the reason there's a step function here is because the agent is switching from the static task to learnable task. You can get away with a smaller and smaller learning rate because you're able to predict the future better, if that makes any sense. And if we just extend the horizon a little bit, what we see is the same curve, except now things are shifted this way and compressed, in that the longer you're going to do something, the lower learning rate you should be able to tolerate from a rational point of view. Okay, so some quick limitations. This is dense computation, so it's not tractable for many more trials or control signal identities, which would be like tasks or strategies, and intensities, which is how much control you're allocating. This in theory could be done, except that it would take an enormous amount of computational power. So obviously this is not the way to do it. In the current model, automaticity depends only on task choice and not performance. Obviously, performance should come into play into how you're absorbing information from the world. And the accuracy functions are arbitrary, again, but this is just a modeling choice. So where can we go from here? Well, we can substitute in decision processes that can describe, real world decision processes such as drift diffusion models, where you can take the parameters and treat them as proxies for control, identity, and intensity. So for example, the drifted threshold. You can investigate whether there are solutions to an optimal control trajectory. So, if I have a certain landscape, can I have some idea of what would be my optimal choice of tasks and control over time? Can I develop that as a sort of prior? And this is actually some work that a student of Andrew Sachs's, Rodrigo Carrasco, is doing right now. He's like a math genius. And I'm really excited for those results. Or simply just writing this model as an RL agent to sort of map out the terrain for more and more complex environments, so to speak, and seeing if we can replicate those results experimentally. I just want to quickly say that I was pushing this direction because I did some rat work during grad school showing that rats could basically prioritize learning over instantaneous reward, which was nuts because they're so impulsive. I'm not saying they're doing this consciously, but there was something in their brain pushing them to do this. Currently trying to do it in humans, but human behavior is a lot more subtle and complicated. But yeah, I think falsifying theories, taking them seriously, and then finding what's exactly wrong about them is exactly the right thing to do. So I'll just thank my two collaborators on this, Sebastian Muslik and John Cohen, and some of the funding that I had.